here we will discuss the delta function well. So to start delta function well, first you have to know what is Dirac delta function. So Dirac delta function is defined as 0 if x not equal to 0 and infinite when x equals to 0. So it is infinite at x equals to 0, and also the integration over all space is equal to unity. So also there are some characteristics of Dirac delta function. The most important characteristics is that suppose fx delta minus suppose a dx will be f. Okay, so now we can start our main problem. Suppose a potential is defined as Px equals to minus alpha delta x. Okay, so easily you can understand where the potential is 0 and where it is infinite. Now let me write Schrodinger equation. So now we will solve Schrodinger equation for Dirac delta function. So potential is plus V psi. So here potential is V is minus alpha delta x, right? And psi and E psi. Okay. So in the previous lecture already we have solved a problem with potential barrier. There you have seen that we have considered actually two conditions. One is for bound states and other one is for scattering states. So here we will start with bound states. That means here when E less than 0, right? I call it bound states. So so we first look at for x less than 0 and then for x greater than 0. Okay, so for x less than 0, so simply Px is 0 from the Dirac delta function definition. So now the Schrodinger equation will be in a simplified form. Okay, I am writing in simplified form. Will be 2me by h cut square psi. Suppose I am defining it k square psi. Okay. So what is k here? K is minus 2me by h cut. Okay. Now you know the solution of this type of equations. So doing this type of problems, you will be familiar with the solutions. The more you will do solve your problems, the more you will be accustomed with this type of solutions. Okay, so the solution will be of the form of a exponential minus kx plus b exponential kx, right? Now look at this function, I mean psi x. Now if you, so now you are considering the region which is x less than 0, right? So towards the negative side you can put x equals to minus infinity, right? Suppose if you put x equals to minus infinity, then you can see this term, right? A exponential minus kx will go up. That means it will give some infinite value, and for that value we cannot normalize our function. So this is not physically acceptable solution. Okay. So psi x will be left with only this part. So that was for x less than 0. Now for x greater than 0, you will get, what will you get? Suppose in the same way, okay, I am writing the main solution of the form of, suppose it is f and g. Okay, somehow it is not focused, right? Yeah, focused. So let me write it. F exponential minus kx plus g exponential kx. So and in what we have done in the previous section, we have put x equals to minus infinity. For in this case, for x greater than 0 region, we will put x equals to plus infinity. Now if we put x equals to plus infinity, then this part will go up. So the psi will be left with f exponential minus kx only. Okay, this part. If you put x equals to infinity, g will blow up. Now so we have got for x less than 0 is something exponential kx, and for x greater than 0 it is f less than exponential minus kx, right? So now so if I suppose write in a compact way, you will get, if I write compact way, means if I convert these two solution in a one constant, parameter term, again it is not focused. So if I write constant, suppose one parameter exponential minus kx, it is for x less than or equals to 0, and it is for x greater than or equals to 0. So from this relation, now there is a confusing thing that for both the x equals to 0, we get this type of equation, because if you see Dirac delta function, it looks like, it is, there's pi around the sphere around the x equals to 0. It is going asymptotic to infinite. Okay. So now we will try to find out this constant by applying the boundary condition. Now you know that the boundary conditions, that at the boundary it is psi is continuous always, but d psi dx is only continuous if the potential is not infinite. If it is infinite, then it is discontinuous. So just in a short note, we will try to see that what happens if we see d psi dx at the boundary. Okay, that if you suppose okay, if I write in this way, you can understand. Suppose I am psi by dx, okay, plus I am integrating the Schrodinger equation. If I limit this epsilon tending to 0, then easily I can get the continuity equation, right? Psi x dx. So now you can see that this last integral, this one, simply will give 0, right? You know better that because there is no such this will behave as a constant term and will give the integration to 0. Just we will left with this term and this term. So if I again write in this way, d psi dx is plus infinite minus d psi dx, it is minus infinite 2m. This one same. Okay, now let's do this part, and I'm taking this here, multiplying by this term. You will get, suppose, 0, because I am trying to find out the differential equation. So it is epsilon Vx psi x dx, right? So it is visible, yeah. So now, okay. Now if I replace Vx, what was the Vx? That was minus alpha delta x, right? If I replace by this, and if I apply, suppose I am replacing 2m h hat square limit epsilon tending to 0 minus epsilon and v is equals to minus delta x psi x dx. Okay, so how will you get? So already we have shown the characteristics, one of the characteristics of Dirac delta function, and if you recall that function, I mean that one, if you recall that one, that fx delta fx delta x minus a and some function, it will keep 2m h part square, so minus alpha multiplied by minus alpha, and it will keep psi 0. Okay, by applying that characteristics or that formula. So you got this equation. Okay, now if you derivative the previous functions, previous solutions, these solutions, okay. Suppose d psi dx equals to so b k, okay, exponential kx, and other one is d psi dx minus b k exponential minus kx, and it is for x less than 0 and it is for x greater than 0. Okay, so it's nice. So from there what I will get, this is minus, right? So at 0, at x equals to 0, I will get, so okay, so if I define, suppose d psi dx minus bk, just put x equals to 0, so then at x equals to 0, I am trying to calculate the values. D psi dx tending from the plus side, it will be a k, right? So very good. So that means, so this delta d psi dx will be 2 dk. So delta, so now if I write d psi dx, we will give minus 2 bk, just taking the difference. Okay, and also psi 0, so simply it will give b. Now if you put here psi 0, we will give b. You can understand. So now I can write, so this is d psi dx, delta d psi dx equals minus 2 bk equals to, already you have written 2m alpha minus, there is minus h cut square psi 0. If you put all the values, this will give. Now if I simplify directly, so k 2 psi 0 also will be bb, and so this will give m alpha by h cut square. Okay, so simply I can now so I can now, hello, so I can write energy minus h cut square k square by 2 square So it will give m alpha square by 2 h cut square. That is replacing by k. So if you normalize psi, so already you have got psi, right? So if you normalize psi x dx equals to 2b square 0 to infinity exponential minus 2a dk. So okay, so now okay, so b square by k equals to 1. So b will be root over k, sorry, m alpha by h cut. So this is the normalization factor b. So you have got b, so easily you can understand what is psi. So if I write psi x equals to m alpha by h cut exponential minus m alpha x by h cut square, and energy is I have written already m alpha square by 2 h cut square minus, there will be a minus. Okay, sorry, there was also plus. So this is the wave function for the bound states. So next we will find out for the condition E greater than 0, that is for scattering states. So now I will calculate psi for E greater than 0. So I will follow the simple logic whatever we have applied in the previous section. So we write the original equation psi, it is for x less than 0, right? So solution k is simply k, you know what is k, 2me by h cut. Okay, so psi, so simply psi will be, you know, here the difference is that here will be it is a periodic function because of k. So a exponential I kx plus b exponential minus I kx for the solution, for the minus part. Okay, so again for x greater than 0, so you will get psi x equals to f exponential I kx plus g exponential minus I kx. Okay, so again you will apply the continuity of psi x at x equals to 0. So if I apply continuity, so that will give a plus g equals to a plus b. Okay, so now I take the derivatives. So it is continuous at x equals to 0, but it is discontinuous at x equals to 0. So I will find d psi dx equals to I k f exponential I kx minus g e I kx. Okay, so simply d psi. So now you need to calculate d psi dx for x greater than 0 and x less than 0, and then putting x equals to 0, you can calculate the limiting values in the plus side and minus side, and in this way you can calculate delta d psi by dx. You can see here it is written. So from this equation now you can calculate f minus g, and reducing the equation in a new parameter define it as beta equals to m alpha by h cut square by k. Now here you have to understand one thing. Now if you consider the wave is coming from the left side, then for the h greater than 0 region, you don't need to consider g, because if you look at the waveform, then you can see here in the g form there is exponential minus I kx, and it is indicating some left towards wave. So for in the case of scattering, where is e greater than 0, so this part should be 0. So now we consider here g equals to 0. If I put g equals to 0, now we can easily interpret the thing. Actually, we can understand the physical meaning of the waves. For the x less than 0 region, A will indicate the incident wave, and B will indicate amplitude of incident wave and amplitude of reflected wave, and similarly F will indicate the transmitted one. So by this from this equation you can easily calculate these relations, and also you know that what is the coefficient of reflection and coefficient of transmission, and this way you can calculate and can verify that R plus T equals to 1. So thank you, that's all.